Right now we're going to go over work. There are several different equations that you can use to define work. The first and foremost that I would suggest that you always think about it is as a change in energy. Now the reason for that is because there are often situations in the MCAT where it's not very clear how work is being done, but it can be very obvious that work is what is causing a change in energy. For example, as somebody jumps out of a plane, they have a value of potential energy. And as they accelerate towards the Earth, that potential energy is converted into kinetic energy. And it's actually work acting on the guy who jumped out of the plane that is causing our change in energy from potential to kinetic. And that change in energy is caused by the force of gravity acting on our man and pulling him down towards the Earth. And that brings us into our second equation for work. Second equation for work is simply that a work is a force exerted over a certain distance. Now oftentimes in the MCAT or in MCAT prep books you will see this as cosine theta. Now the reason for that is because work is caused by a force that is exerted parallel to the displacement of an object. So for example, if we've got an object sitting on a table and sliding across the table to the right, then if there was a force acting on the table towards the right, that force would be exerting a work in that distance. Now let's say in this case that we were exerting a force against the object, but the object was still sliding towards the right. So in this sense we would be slowing that object down as it slid towards the right? Now this force may have the same value, but in this case it will be doing negative work rather than positive work because it's acting to slow down our object's displacement. Now let's take it one step further. Let's say that we were exerting a force by pulling this object with a tension force at this angle to the horizon. If this were the case, we can see that there are two components of the force here, an x component and a y component. Now there is a y component of the force, but we can see that this y component is not actually accelerating our object upwards at all. That force is not significant enough to change our object's displacement in the y direction. On the other hand, we do have an x component of the force that is changing its displacement in the x direction. So in this case, we do want to use the x component of the force and not the y component of the force, because it's only the x component of the force that is contributing to a change in displacement in the x direction. So that's the reason why you usually see force times distance cosine theta. Now personally, I don't worry about the cosine theta part. I always draw a picture and then use some basic trigonometry to find the value of the force that is acting parallel to the displacement of my object. Now the next equation for work is equal to pressure times the change in volume. Now I want to point out this equation. This is one you're generally going to see more in chemistry scenarios where we're changing the volume of gas, but it's important to point out here so that you are aware that this equation is equally valid for work. Now the reason why this equation works out is because of the units here. The SI units for pressure are in pascals, which is newtons per meter squared, force over area. Multiply that by meters cubed for volume, and the meters squared on the bottom we're going to cancel out with 2 of the 3 up here. And so we're going to be left with newtons times meters, which you'll notice is the exact same units that we're using up here. Force, newtons, times displacement in meters. So this equation is equally valid. You'll just use it in different scenarios. This one will be used in 3-dimensional scenarios, whereas this will be used in 1-dimensional scenarios. So now let's go ahead and walk through a few practice problems regarding work. Now the first problem we're going to do is actually going to touch on some subjects that we haven't gone over together yet. So I'm going to provide you some equations that you might need. The equation for the electrostatic force acting on our electron in this case is going to be the charge of that electron times the value of our electric field. The value for potential energy is going to be the charge of that electron times the value of the electric field times the distance our electron is separated from the plate it is traveling towards. So keep these equations in mind. You may use one of them, you may use both of them. I just want to provide them since you haven't learned them yet. But you will learn them later on in the program, and at that point it may be valuable to you to come back and revisit this question and see how well you do at coming up with the equations you need to do well on a problem like this. Now I need to give you a little bit more information so you can solve this problem. So let's start off with the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. And don't forget my little trick, E is just the calculator shortcut. It doesn't actually mean the natural log version of E. So times 10 to the negative 19 coulombs is the charge of our electron. And in addition to that, the mass of our electron is 9e to the negative 31 kilograms. Now we'll say that the distance between our electron and this far plate is 2 millimeters. Now all you need to understand about this for now is that an electric field going towards the left will cause our electron to move towards the right. Okay, it would cause positively charged objects to move towards the left. But again, don't worry about that too much for now. We will cover that in detail later on. And then finally, we'll say that the value of your electric field will be 10 volts per meter. So I'm actually going to ask you to solve for two questions here. Number one, I want you to solve for the work done on our electron as it travels this 2 millimeter distance from here to our plate on the right. The second thing I want you to solve for is the velocity of the electron just before it hits this plate on the right. So go ahead and give that a shot, and we'll go ahead and talk about it. So the first thing I hope you thought about when considering work was that it's a change in energy. I hope you recognized that this electron is starting out with some value of potential energy, and that over time it is converting that potential energy into kinetic energy. And it's the force acting on our particle over this distance which is going to be doing work and causing that change in energy. So since we want the value of that change in energy, there are a lot of different ways we can think about this. We can calculate the final amount of kinetic energy gained, and that would tell us the value of our change in energy. Or we could simply start out with the initial potential energy and understand that all of our potential energy will be used up and converted into kinetic energy by the end, which means that all of our potential energy represents our total change in energy. So essentially we can set up our change in energy equals QED and then solve for work that way. So Q is 1.6 e to the negative 19. Our electric field is 10, which is simply going to make this 1 e to the negative 18 times our distance. And our distance is 2 millimeters, but be very careful about the millimeter units. We need to convert that into meters, so it's going to be 2 e to the negative 3 meters. And then we can do our math, which will give us 3.2 e to the negative 21. And energy is always measured in joules, so there we go. There's your answer. So now for the second part of this problem. If we want to solve for velocity, we want to consider kinetic energy. So kinetic energy is also going to be 3.2 e to the negative 21 joules, because all of that potential energy is going to be converted into kinetic energy due to the force causing this change in energy, or work, over this 2 millimeter distance. So we've got 3.2 e to the negative 21 joules of kinetic energy, which is equal to 1/2 mv squared. We have our mass, so we'll plug that in and solve for our velocity. Let's go ahead and do that. So 3.2 e to the negative 21 times 2, I'm going to carry this over, it's going to give us 6.4 e to the negative 21. And 6.4 divided by our mass, which is 9 e to the negative 31, is equal to our velocity squared. So now looking at this, 6.4 divided by 9 is going to give me about 2/3. So I'm just going to round that to about 0.66, but keep in mind that there's a little bit more than that, so I'm going to bring it up to 0.7. So 0.7 will be an accurate enough fraction, and in this case, negative 21 minus negative 31 is going to give me e to the positive 10. And all of that is going to be equal to my velocity squared. Now since I'm going to end up square rooting a number like this, I want to make this number look a little bit better, because that's a pretty ugly number to deal with when squaring it. But now I'm not going to want to actually change the value, I just want to move the decimal around to make it a little bit more manageable. So now let's say that I moved it to 7 e to the 9. If you make one number bigger, you got to move that other exponent to make this number smaller again, essentially, right? Now 7 e to the 9 makes it a little bit better for 7. Now that number is a little easier to square root, but now we would be essentially dividing 9 by 2. Because whenever you raise exponents to their powers, you end up multiplying or dividing them. In the case of a square root, it's the same as multiplying the exponent of 9 by 1/2. In this case, if we were to do that, we would end up with some number times 10 to the 9/2. We don't want to deal with a number like that on the MCAT. So what I'm going to do is I'm going to move this decimal place over one more, so that way this can be an even number again. So that way when we divide it by 2, we'll get a nice whole number. So 7 e to the 9 is going to become 70 e to the 8. And now we can take the square root of that fairly simply. Square root of 70 is going to be barely over 8, right? Square root of 64 is 8, so just a little bit more than that. It's definitely a lot less than 81, which would give us 9. So I'm going to estimate it at about 8.2. And the square root of times 10 to the 8 is going to be times 10 to the 8 divided by 2, which is going to be times 10 to the 4th. And there's your answer. So the velocity of this electron by the time it hits that plate will be 8.2 times 10 to the 4 meters per second. So go ahead and stick around for one more practice problem regarding work, and we'll go ahead and walk through that one right now. So let's say here that we've got a block that weighs 5 kilograms, And let's say that some initial force is applied to it that allows it to start sliding across this plane at an initial velocity of 10 meters per second. Now what I want you to do is find out how far this block is going to slide before it comes to a complete stop if the coefficient of kinetic friction for this surface is 0.2. So go ahead and give that a shot. Okay, so for a problem like this, you actually have to keep in mind both of our conceptual definitions for work. Understand that it's both a change in energy as well as a force exerted over a distance. And keep in mind that there's that cosine theta element to work as well, but I'm just going to go ahead and think about that conceptually and understand that my work again is exerted parallel to the displacement of my object. So in this case, what type of energy is our object starting off with? You should have answered kinetic energy. It does have velocity and therefore has kinetic energy. So let's go ahead and calculate that. 1/2 mv squared. It's going to give us an initial velocity of 10 meters per second. Square that, it's going to give us 100 times 5 kilograms. So 500 divided by 2 gives us 250. So we start off with 250 joules of kinetic energy. Now, what type of energy are we going to end with? Well, we will end with potential energy, but we'll end with the exact same amount of potential energy as we started with, right? Because it's going to end at the same level or same height as it started with. And it will end with 0 kinetic energy, which means essentially at the end, the only difference in the two energies will be the loss of this kinetic energy. That represents our change in energy, which again was caused by our work or our force over that displacement. So we can set this equal to our force times our displacement. So now since we're solving for displacement, we need to find our force. So now what type of force is acting on our object over this distance? You should have answered that it was a frictional force. And what is the equation for frictional force? Well, you should have answered that our equation for frictional force is equal to mu k, which is our coefficient of kinetic friction, times our normal force. And our normal force of the object, if you remember, is just mg. So essentially, we've got mass times gravity times our coefficient of kinetic friction. So let's go ahead and solve for our frictional force. So our frictional force has a 5 kilogram mass multiplied by 10 meters per second squared for our gravity, which is going to give us 50. And 50 times the value of 0.2 is going to leave us with 10. So the value of our frictional force is 10 newtons. So now let's go ahead and plug 10 newtons into our equation for force here and solve for displacement. So that will give us 250 equals 10 times our displacement. So when we solve for displacement, we will get 25 meters. And there you go. This is a great example of how the MCAT can test you on both conceptual definitions of work, both being a change in energy as well as a force over displacement. Now keep in mind technically that this force is acting in the negative direction since it is opposing the direction of our object's motion, but it doesn't really matter. That just indicates that our work will have a negative sign on it, but keep in mind that that negative sign is a totally arbitrary value. I've never seen a question on the MCAT before that is giving you two answers that are exactly the same and only differ by the value of their sign. So don't worry about those. Really you'll be okay using whatever signs you want. Just make sure that you're consistent with whatever signs you choose.